Today's topic, as you see, is on multilinguality, multimodality, and large language models. So in natural language processing, especially for language, we revel in ambiguity, right? We purposefully keep things ambiguous. So I don't know how you interpret the title. Is it multilinguality, multimodality for large language models? Is it large language models uh, processing multilinguality, multimodality? It depends on you, okay? You interpret the way you want. So it's a broad topic. Lots of, let's say, concepts, issues, challenges involved in dealing with multimodal information, multilingual information. Our country satisfies all the three conditions of velocity, volume, and variety when it comes to language data. And there are many problems involving text, which now it is understood require multimodality. You need to look at the picture. For example, for sarcasm, we have to see the tone of speech again to understand sarcasm. And sarcasm is not a esoteric problem anymore. It has actual practical application. The conversational AI agents, the chatbots need to be sensitive to sarcastic remarks, okay, by customers, let's say. And good chatbots directly benefit business. There are lots of data, and we have been interacting with the airlines industry, e-commerce industries. They say that give us empathetic chatbots, which understand nuances, which understand emotion, sentiment, and so on. Okay, so all these are very practical proposition. Natural language processing, which used to be a very back-end and lab situation problem, is now out in the open with immense mm, applications. Okay, so let's proceed. And I have a very happy situation, Mac. I hardly get to speak for 3 hours. Okay, I get 1 hour, 45 minutes. So there are many speakers, so uh, you know, limit your talk to 1 hour and so on. So now I have 3 hours. I just feel so comfortable about it. I'll go slowly. Okay, and the advantage of slow speed is that you can communicate insight. Okay, it is you all of you are in a situation in a world where information is available in plenty. Proportionally, insight is so rare. Okay, so insight requires experience, lots of failures, lots of successes. So I'd like to communicate some of these to you. All right, so let me start with a poem that I wrote. Okay, this is a poem I composed. This is ode to scientists and engineers. Scientists ask why, engineers ask why not. Hmm? Scientists wonder at what is, engineers wonder what could be. World could not do without either. Scientists study, engineers make, and ever the twain shall meet. So what I'm trying to communicate through this poem is that both scientific insight, okay, and engineering design implementation, both are important. Both should go hand in hand. Strong, complex implementation should be supported by very clean theory as far as possible. And similarly, the theory and conceptual understanding should see the light of the day through implementations. That is the main idea. So as we go along, you will see that I am continuously referring to language phenomena or phenomena in the real life. Their modeling, their implementation, numbers, analysis, and so on. This is what machine learning people do all the time. Unfortunately, the emphasis on phenomenon, understanding the task, understanding the phenomenon, is not so much there. So this is something we would like to see is important. So I would like to spend quite a lot of time on introduction and perspective, the foundations, and really basic concepts. We would like to understand nature of language and NLP. What is human language after all? and what implication does it have for NLP? Multilinguality and multimodality, what are these concepts after all? What is multilinguality? Okay, what happens when we introduce multimodality? How should they be introduced? Now, those kind of questions we need to understand. Language modeling, it's a very popular term. And since the time statistical natural language processing started, uh, the, phrase language modeling started becoming more and more important. But the problem of language modeling or the concept of language modeling is as old as 2000 years, at least. Okay. So in language modeling, the question is what string of words belongs to a language? Okay, if I give a string of words and ask you, is it English or is it Spanish, Hindi? You have a decision procedure in the mind which tells me that, well, this is a valid string of a language. Okay, so this is the notion of language modeling, and language modeling has changed its form over the years. Language modeling is expressed in many different ways. Then LLMs are very sophisticated machinery, though the underlying theory is simplicity itself. And how are they used in practical applications? We have 3 applications in our lab, which are supposedly impactful for society. I'd like to talk about them going forward. One of the success stories of LLMs is conversational AI. Okay, ChatGPT, everybody uses ChatGPT, but the foundation is really LLM. Then pragmatics and capabilities of LLMs, I see, all over the world in many research groups, the interesting question being asked of, does LLM have such and such capability? Can LLM do morphology? Can it do part of speech tagging? How about pragmatics, okay, which is at the highest level of NLP stack? We have some research in investigating the pragmatic abilities of large language models, and then we'll draw some summary conclusion, look at the future outlook, and so. There's a roadmap. Let's see how much we can do. So first of all, what is language? And I always begin my course and talks where I have sufficient time with this slide, trying to understand what is human language after all. Okay? What defines human language? So there was this seminal book in 2003 by George Yule from England. He is a cognitive scientist as well as a linguist. This book is called Study of Language. So there are 6 properties, he says, which defines human language. The first property is displacement, then arbitrariness, then productivity or creativity, cultural transmission, discreteness, and duality. So these 6 properties of human language are always out there. They are in the background. You cannot ignore them. Okay, you may not. You may be ignorant that of these properties, but they are always there influencing our decisions with respect to language, any activity with language. So first property, which has been extremely difficult to tackle, especially when it comes to pragmatics, computational pragmatics, is the problem of displacement. Human beings have this remarkable instrument by which they can talk about places and times when they are not actually present at that place at that time. If you look at this sentence, I saw him yesterday at the market. When I am speaking, I am not in the market, and I am also not present in the yesterday. I will see him tomorrow in the school. Again, I am not in the school at this point of time when I am speaking, and also tomorrow has not arrived yet. Okay, so we are able to express and talk about times and places without physically being present at that time and that place. This is called the displacement property. And there are documents, papers saying that animals are always here and now. Their life revolves around here and now. Okay, so this is a very interesting property, and this leads to creativity, imagination, which defines human beings. And without that, research also is not possible. Okay, you remember the phrase, "What could be?" Engineers ask, "What could be?" So, what could be is a matter of imagination. So, displacement is a remarkable property. Do remember this when you build NLP systems. Okay, conversational agents, are they able to handle times and places when they are physically not there, and vice versa. Okay, when they're placed in an environment, can they pick up the signals of here and now? The next property is arbitrariness, which is the quarrel between sound and meaning. So why is water called water, water in English, jal in Bengali, pani in Hindi, tanni in Tamil, and so on, aqua in Latin? So these names have no connection with the meaning, except for a set of words called onomatopoeic words. Okay, the word hiss, for example, has the meaning and the sound which are correlated. Hissing of a snake. Then productivity is also referred to as generative grammar. So, a finite number of symbols and rules can produce infinite number of sentences. And that happens due to a property called recursion and embedding. I can embed sentences within sentences. Okay. The cat that spilled the milk, which was warm, okay, and so on, fled. So subject is cat, and fled is the main verb. Between cat and fled, there has been an arbitrary amount of text. And you can go on embedding phrases and clauses like this. Of course, the sentence will not remain natural anymore. Okay, and human cognitive abilities also will not be able to process them. But uh, you can be extremely productive with respect to sentences. Cultural transmission: a child acquires the parent's language, which is also something we take for granted, but has a lot of mystery behind it. Why does a child pick up the language of the parents? Then discreteness is the fact that sound and meaning units are separated. When I speak, produce continuous speech signal, but the hearer is able to identify word boundaries, even if explicit pause is not given. Okay, sentence boundaries are detected, phrase boundaries are detected, even though there is no break in signal. Okay, surely meaning and pragmatics are playing a role there. And the final property is duality. The surface structure and deep structure are often different in language, mainly because of ambiguity. And there are difficult and very challenging problems like metaphor, sarcasm, where the surface meaning and the deeper meaning are often opposite to each other. So these are the 6 properties of human language, and natural language processing scientists, engineers should be aware of these properties, okay, and the implication that they have for any kind of theory and implementation. Now, we would like to understand what is language phenomena, okay? What is the meaning of language phenomena? So there are phenomena in the language. The first example given is the Sandhi phenomenon. This is phonetic and phonological transformation at morpheme boundaries. The example I've taken is from Sanskrit. Guru plus Adesh through Sandhi becomes Guru Vadesh. Okay, so we introduce a semi-vowel wa at the boundary of Guru and Adesh. U and A together produce wa sound. Also, a full ra sound, a complete consonant, has become half consonant in the Sandhi output, right? So these are called language phenomena. A full consonant becoming a half consonant, 2 vowels um, being absorbed as a semi-vowel. These are called language phenomena. So this is at the phonological, phonetic level. At the syntax level, you see language phenomena. For example, fronting of verbs in question formation in German. So in German, you say trinkst to do Tee. Do you drink tea? So here the main verb has moved to the front of the sentence. In English, the phenomenon is different. In English, the auxiliary verb moves to the front of the sentence, not the main verb. You have to propose is, do, etc. And they take the morphological transformation and come to the front. So this is a syntactic phenomenon. And then there is semantic pragmatic phenomenon. An example of that is sarcasm. So this sentence is my favorite. Um, an unattended invitee leaves the party and the host asks him, how did you enjoy the party? By that time, the person is very frustrated, angry because nobody was caring for him. And he says, oh, I love being ignored. So this sentence is sarcastic. It has a positive sentiment bearing word love and negative sentiment bearing word ignore. Their presence together indicates inconsistency, incongruity, and that is the signal for sarcasm. Okay, so these are language phenomena, and the language phenomena are actually myriad. Okay, look all around you, you will see language phenomena happening all around us, and a trained linguist, a trained NLP researcher would spot those phenomena and wonder about them, what to do about this. Sarcasm is no longer an intellectual problem, practical problem. Customers can leave services and organizations if their sarcasm is not caught by the chatbot. Okay. So about sarcasm, we in our earlier research we found that 11% of the tweets are sarcastic in nature, especially those which are political in nature. And out of those 11% tweets, 17% are numerically sarcastic, where the sarcasm arises because of a number. So I love my phone, it has only 5 minutes of battery backup. Would you love such a phone? Maybe not, really. So this is sarcastic because of the number 5. I love my phone because it has 5 days of battery backup. I indeed love such a phone. Whatever the opposite case, I hate my phone which has 50 days of battery backup. What is that phenomenon? This also exists. Okay, so we, while doing our research on sarcasm, we found that, and a very interesting kind of error was occurring, because those sarcasm detection algorithms are based on incongruity. So are there entities in the sentence which are incongruous with each other? I love being ignored, love and ignore are incongruous. So we had an opposite phenomenon. Okay, for a sentence like, oh, my life is miserable, I have to give 1,000 autographs every day. Is his life miserable? He's actually bragging. Okay, so this is called humble bragging. We introduced this phenomenon called humble bragging. This is a much, much lesser percentage compared to sarcastic sentence, but it exists. And when an NLP system encounters such a situation, it has to understand. So we call this humble bragging. Now, how do you deal with incongruity computationally? We deal with that through word vectors and their similarities. Okay, so that's a separate discussion. Feel free to, interject, comment, question anytime you want. Okay. Now, language phenomena we understood. There are different kinds of language phenomena at syntactic level, phonetic level, morphological level, and so on. How do we model language phenomena? Because a computing machine will understand the model. Okay, it has to be modeled. And the purpose of modeling is to represent a phenomenon and make predictions based on understanding of the phenomenon. So modeling of language phenomenon is done by softmax. Okay, softmax and sigmoid play a crucial role in natural language processing, which is based on machine learning and data. So softmax function definition, if I'm given a vector, then the output of the softmax is defined by this equation. The ith component of the softmax output is e to the power, the ith component of the input vector, divided by this normalizing quantity, summation of j from 1 to k, where there are k components in the input vector, e to the power zj. This is how softmax is computed. The effect of this is that it converts any vector into a probability distribution effectively, right? Each component is between 0 and 1, and their sum is equal to 1. So modeling language phenomena, in this enterprise, the first role is that of softmax, which converts vectors to probability distribution. Very important. So here's an example. If z equal to 1, 2, 3, then z1 is 1, z2 is 2, z3 is 3. You raise them to the power of e, divide by their sum, and you get the softmax output here. The second player in the modeling of language phenomenon is the cross entropy. Softmax and cross entropy go together. Softmax produces a probability distribution. There is a target probability distribution and an obtained probability distribution. We need to find out the distance between them. That is measured by cross entropy loss. So cross entropy loss involves two entities. One is the number of classes, and the other is the number of instances. So we take an instance x. X is going from 1 to n. These are data instances. So x, and the probability of x belonging to the class k goes from 1 to the number of classes. So pxk log qxk is, and minus of this whole sum is called the cross entropy between two probability distributions. So we have a target probability distribution, we have a observed probability distribution, we have to measure the distance. This is the cross entropy. That distance is called a loss, cross entropy loss. So is it okay? The first player in this game is softmax, second player is cross entropy.
For softmax,
Ah.
so I got a very huge vocabulary. But softmax won't be able to make certain vocab zero, words token zero. So it will cause issue, right?
So we are talking about maybe the skip-gram SIBO situation or decoding situation where the next word has to be predicted, and we have to pick up that word which has the highest probability based on the autoregression and conditioning. So since there are so many entities, the probability distribution has very small values, right? Component wise. That's it. That is what it is. And it can cause underflow, etc. So in such cases, it is all right to work with log. Okay, log loss. So log loss actually saves you this underflow problem. Okay. So the second player is cross entropy. And then the third player is backpropagation, okay, where the weights have to be fixed. So I'm sure each of these components you know very well, but how they come together to form a picture is important, which is what I wanted to present to you. So softmax, cross entropy, and backpropagation, they together form a learning machine. And this learning machine is very suitable for language processing. So here is some mathematics, but they're actually quite simple if you look at the implications. So this L is the loss, which is cross entropy loss, and it is shown for a single neuron. For single neuron, the equivalent of softmax is sigmoid. Sigmoid gives you a value between 0 and 1. And so therefore, sigmoid can be looked upon as a probability computer. Just like softmax computes probability for multiple classes, sigmoid computes probability for 2 classes. So this L is the loss function, and I am interested to find out the weight of this connection, which goes from x1 to this neuron. Then I apply a chain rule because L does not directly depend on W1. So introduce all the intermediate variables. And when we systematically go through these derivatives, we come to an expression for weight change, which is learning rate eta the difference between target and observed and the input value. This is the basic backpropagation rule. The interesting thing here is that when you combine softmax and cross entropy, the derivative of the neuron does not play a role, which is a very interesting point. If you work with total sum square loss, then the derivative of the sigmoid appears in the weight change rule. In case of softmax cross entropy combination, this O into 1 minus O, which is the derivative of sigmoid, gets cancelled with the derivative of the sigmoid here. Okay, so that's an attractive proposition for softmax cross entropy combination. So this was the third player. And when you have multiple neurons, then you will have to use softmax at the output. And you will have to work with the Jacobian of the net input to these neurons and their output. And when we go through the derivations, we find that again, the weight change rule is eta into difference between target and observed multiplied by the input value, same as sigma neuron. And here also, the derivative of this softmax neurons get cancelled through denominator up and numerator cancellation. Okay, so for softmax as well as sigmoid, the weight change rule is uniform. Learning rate into difference between target and observed and the input value at the connection. So this is another instrument in modeling of language phenomena. You know, an enormous number of applications where you just have the training data and the classification level for the training data, or sequence to sequence mapping, input sequence, output sequence. And this is completely modeled, okay, with the softmax cross entropy and weight change by backpropagation. Okay, so this is a very fundamental point for all NLP researchers. If you have any question at this point, ask me. If you have any doubt, any question. This is an NLP researcher's bread and butter. Okay. So when we do this modeling of language phenomena, the final step is winner take all. Produce as output that quantity which has the highest probability. That is the only rule which has the highest probability. When you are doing sequence to sequence mapping, decoding, and there is a production of a word based on autoregression, self-attention, cross-attention, encoding of the input vector, whatever be the situation, it is the highest probability entity which is produced. So that's a very hard decision, black and white decision. Whichever has highest probability, produce that. This is the winner take all strategy. Now, the example here is that of sentiment analysis. Sentiment analysis has three classes: positive, negative, and neutral. I like the story of the movie Positive Sentiment. However, the acting is weak, negative sentiment. The protagonist is a sports coach, neutral sentiment. It's a fact. So the training data will look like this. For sentence A, the sentiment is positive, so 1, 0, 0. Sentence number B, negative sentiments, so 0, 1, 0. Sentence C is neutral, 0, 0, 1. See that in the target labeling itself, we have defined a probability distribution where the probability mass is totally concentrated on one class. Right? Okay, you see that. So this is with respect to annotated data, human beings are creating this. But when a deep neural network system or any neural network system is producing an output with respect to classification decision, they produce these kind of values. 0.09, 0.24, 0.65. Why can't they produce 1, 0 values? Why can't softmax or sigmoid produce 1, 0 values? Yeah. So sigmoid reaches a value of 1 at plus infinity, 0 at minus infinity. Those are unreachable points, right? So they will never produce 1, 0, but close to 1, 0. Now, out of these, we see that the neutral sentiment has the highest probability. So our classification decision is that. even if it is not close to 1. So from here, we can make out that if we are not close to the distribution 1 and 0, then the error value is high. Okay, so that means the training has not taken place properly. So this is the training data, okay, and finding the error is through loss function, total sum square loss or cross entropy loss. Now maybe the class would be interested in asking, when is cross entropy loss appropriate? When should I use total sum square loss? Maybe the answer is known to some of you, but this is a frequently asked question and students are often at a loss. When should I use which one out of these two popular loss functions? The answer is simple. Total sum square loss should be used in case of regression, okay, and cross entropy loss should be used for classification, okay. Again, if the classification is a multi-class classification problem, so if imagine a emotion detection situation, a sentence has both joy and surprise, sadness and disgust, anger and sadness. This happens, okay, in case of emotion and sentiment analysis problems. So then we do not have a probability distribution because the labels are such that the data has multiple ones, more than one. So it is not a probability distribution as such. Unless you apply some kind of pre-processing, you do a pipeline processing, stage processing. First detect sadness, then detect disgust, and so on. Okay? But in case of multi-class classification problem, you cannot apply cross entropy loss directly.
We can have sadness, happiness. According to the highest probability, we can use
but you are not dealing with the probability distribution anymore. So take the label data. So label data will have 2 ones if it is sad as well as disgust. Okay, and then what will you do? Yeah, so you'll have to do something else in that. Okay, so he's suggesting 0.5, 0.5. That will not work. Okay, think about why. Okay, think about this. Okay. So now, after this foundation, where machine learning and NLP interact with each other, okay, in a very interesting way, we come to nature of NLP. We have looked at the nature of language before, now nature of NLP. So natural language processing is art, science, and technique of making computers understand and generate language. This is a very old definition of NLP, since 40s, 50s, I would say. Very old definition. But the emphasis has shifted. Okay? While about 50, 60 years were spent in natural language understanding, the recent times are taken by natural language generation because of generative AI. So when we were students, natural language generation used to be a secondary concern. Okay? And the 3 important parameters of natural language generation were morphology, syntax planning, and vocabulary mapping. Okay, so I eat rice, मैं चावल खाता हूँ. So first vocabulary mapping, I to मैं, right? Rice to चावल, eat to खा, the root verb खा. And then you will have to apply morphological processing and generate खाता हूँ from खा, because it is first person, singular number, and present tense. And then you have to do syntax planning. In English, the main verb was at the center. In Hindi, the main verb has to move to the end. So this is called syntax planning. So those were the only 3 concerns we would be concerned with, okay, for natural language generation. But natural language generation, we know, is much, much more complex. There is what is called nuances, stances, okay, profanity, hate speech, pragmatic concerns, register. Again, my favorite example is if you're writing an application for leave, okay, and in the application for leave, you have to say that my mother is not well, I have to take half-day leave. Can can you say, my ammi is not well, I have to take half a day leave in a formal application? Ammi and mother, they mean the same thing. Why can't we use ammi? Okay, so this is called the register problem. It is not appropriate in that context. That takes us to pragmatics. So natural language generation, and try this on ChatGPT. Okay, you prompt it and say, write a formal application for leave and write an informal statement requesting for leave. It produces that style. Okay, so style in natural language generation is a deep research area. So we have 3 generations of NLP, actually 3.5, I would say. So first generation is rule-based NLP, which is also called model-driven NLP. The model is created by a human being. Modeling means modeling of language phenomena and modeling of task phenomena. Okay, so you have to understand both the phenomenon, language phenomenon, and task phenomenon. A sentiment analyzer for Tamil, let's say, will have to take into account properties of Tamil language as well as what it means to have sentiment. What are the determinants of sentiment, emotion, and so on. Generation 2 was statistical machine learning based NLP, which is when we saw the arrival of hidden Markov model support vector machine for taking up NLP tasks. Hidden Markov model is a contribution of automatic speech recognition to NLP. Okay, Frederick Genilek from AT&T Bell Lab showed that if you have annotated corpus, and if you train a hidden Markov model with this annotated corpus, you can do part of speech tagging with very high accuracy, and it beats any rule-based system. So do you see some parallels happening? This happens, for example, for ImageNet, okay, where convolutional neural network beat data-driven statistical machine learning system hands down. Okay, 3 times, 4 times accuracy by convolutional neural network. This also happened in speech through ResNet. Okay, so every time the data-driven approach upstaged a rule-based approach, what happened was there was a tremendous improvement in accuracy, and people thought that here is a new paradigm. So hidden Markov model upstaged template-based and rule-based part of speech tagging. Support vector machines were extremely successful in document classification. Emotion analysis, sentiment analysis are document classification problem. Do you know what it upstaged? What paradigm did it change in support vector machine? It introduced a new paradigm by replacing keyword-based document classification. Okay, so keywords, you take the keywords, formulate rules based on keywords, and then give a classification system. But it was very brittle and its accuracy was low. Support vector machines, on the other hand, were very, very successful, okay, for document classification. Generation 3 is neural network based NLP. So this is the ruling paradigm now. And slowly, I think it is giving way to generation 3.5, which is large language model and generative AI. Notice that I'm distinguishing between normal neural network based NLP and LLM and Gen AI based NLP. Am I justified? Because LLM and Gen AI are also based on neural networks. Why should we distinguish? Well, we distinguish between them mainly because of the huge number of parameters. This is a completely different scale of parameters. Okay, and also the introduction of layers and layers of neural network and huge amount of resources it consumes. Okay, it's not a different paradigm, but it's a different business altogether because of the resource requirement in terms of data and computing. So this is again my favorite figure, 2 pillars of NLP. Ultimately, an NLP system is a coded piece of software. It's a piece of software. It's a piece of code which runs on machines. So the 2 pillars on which this system rests are linguistics and probability. Linguistics refers to language science. Probability refers to data science. Okay, language science and data science, they come together to produce effective natural language processing system. What is the role of linguistics or language insight, the first pillar of NLP? Well, linguistics plays a very important role before the machine learning model operates. Its crucial role is in preparing data. So deciding on the annotation scheme, if you people have implemented part of speech tagging, then you must have used the pen tree bank tag set. If you're doing post tagging for Indian languages, you must have used the BIS tag set, where IIT Bombay also contributed quite a lot. So those tags were nuggets of wisdom. Why so? Because you have to strike a good balance between uh, many tags and small number of tags. If you have a very coarse tag set, it is not useful in downstream NLP application. If you have extremely fine tag set, then the classification accuracy is very low because the classes overlap. Okay? And again, they are not very useful for downstream NLP application. So designing pause tags is the job of fine linguists, fine linguistic work, insight, as well as computational insight. What is the optimum number of tags? They should be linguistically well-grounded and computationally feasible. And an important document while annotating data is the guideline document. So those guidelines can be created only by people who have language insight, namely linguists. Linguistics also plays its role after the model has operated, namely in interpretation of the model output. So this is also the role of explainability, which is again quite hot these days, but it is linguistic insight which interprets the model output. So here again, my favorite discussion is that when we see any problem with human behavior, uh, it is impossible to understand the source of this problem by looking at each and every neuron and the connection, right? There are about 600 trillion neurons in the brain. So we try to gauge the problem through functional testing. Okay, if somebody has, let's say, um, if somebody is dyslexic, then it will show up in spelling errors, not able to decipher words. So these are functional testing. Okay? So those functional testing, what should be the test suit? Okay, that has to be given by language experts, linguists. Here, linguistics only has to play its role. So I have a good example at my disposal when we were doing statistical machine translation. Okay, 2015, 16 or so, we had some amount of parallel corpus, and there we found that whenever any Dravidian language was involved, okay, in the translation, source language is Tamil or target language is Tamil, the accuracy invariably was low. So this statistical machine translation, you cannot actually trace if some rule is misfiring, malfunctioning. It's not possible, it is statistical. So there is data and there is this Moses system, which is the aligner. And then there is beam search based decoding. How to trace the error? Then the linguists in the team said that the problem is not with the architecture or data or machine learning model. The problem is with the language phenomenon. Okay, so Dravidian languages have very rich morphology. Lots of morphemes are stacked together, and this phenomenon is called agglutination. If you do not handle agglutination, any machine translation system for Dravidian languages is bound to have low accuracy. This is the case for Hungarian, Finnish, Turkish, Arabic. Wherever you have complex morphology, you have to do segmentation and then only do machine translation. This insight could not have come from a computer scientist. Only a linguist can give this insight. What role is played by probability or data insight, which is the second pillar of NLP? It contributes to important conceptual machinery. First is law of large numbers. You know, we always work with probability. The softmax also produces probability distribution. And these probability values are our parameters. So law of large number tells me any probability which is used as a parameter can be trusted if we have sufficient number of data. As the data increases, the probability values become more and more trustable. The confidence in them increases. So this is the law of large numbers. So if you observe from a sample that probability of a noun following an adjective is 0.8, you can trust this probability value only if the data is sufficient. Okay, otherwise not. The second conceptual tool it provides is the central limit theorem, which is so useful. And what it says is that beyond a threshold on the amount of data, we can use normal distribution approximation, whatever be the underlying distribution, to estimate the parameters. So we estimate parameters from the data, right? Can you get probability values without data? No. You always get probability values from the data. And what we do is that we apply maximum likelihood estimate for this. So after that, when we make any conclusions, draw any conclusions about the data, it is often by normal distribution approximation. Okay, and that is allowed if we cross a particular threshold, and this fact is contributed to by the central limit theorem. Okay, and the formal statement of central limit theorem is that if you take many samples from a population and take some average value for a parameter, that average value follows the normal distribution. This is the central limit theorem, right? How this statement applies to our problem? Okay, it's a nice thing to think about. Do that. And also the hypothesis testing, which is again the bread and butter of machine learning, is founded on central limit theorem, finally. Okay, so now the main challenge in natural language processing is ambiguity. Words, phrases, sentences, all of them have ambiguity. So one of the epitomes of an ambiguous sentence is this, okay, which linguists are very familiar with. This sentence looks like a mistaken sentence or nonsense maybe, but it has a meaning. How many of you have seen this sentence before? I mean, those who have done a course with me probably have seen this, and okay, then others also. You have seen it where? Achha. It looks like it doesn't make sense, but it is something. It does, yeah. It has meaning. Okay, so to understand this sentence, you have to get the syntactic structure of the sentence, and to obtain the syntactic structure, you first have to find out which is the main verb of this sentence. So 1, 2, 3, 4, 5, 6, 7. There are 8 buffaloes in this sentence. Which one is the main verb? Then you'll ask, I have never thought that buffalo is a verb. No, buffalo is a verb. The word buffalo as a verb means to bully. Okay, the meaning is bully. And buffalo as a noun has again ambiguity. Buffalo is a place, okay, University of Sunny Buffalo, and buffalo as an animal. Right. So once I have told you the meaning of these words, okay, that buffalo can be a main verb, mean bully. Which one do you think is the main verb here? So I can guess your thinking process. You are ruling out the capital buffaloes. Can't be main verb, right? Yeah. Is it so? But sentences can begin with verbs, and then this could be the main verb. The main verb is this, the third last. Okay. So now let's see what it means. And I asked ChatGPT, what do you understand by the above sentence? So ChatGPT came back and gave this output. Buffalo as a noun refers to the city of Buffalo, which is the city of New York in the state of New York in the United States. Buffaloes can be a verb, means to bully, confuse, or baffle. Buffalo can be a noun, refers to the animal, specifically the American bison. So ChatGPT writes this. Describes a scenario where bison from buffalo are being intimidated or confused by other bison from the same place, who in turn are intimidating or confusing other bison. It's a playful sentence that plays on the multiple meanings of the word buffalo as a place. And this output is completely correct. So ChatGPT could do this, not human beings. What is wrong? Okay. The answer possibly is that ChatGPT has seen this sentence before. Okay, it is crawling lots of data and using this for training. And therefore, this sentence it must have seen from somebody's lecture. It could be my lecture also, which is there on the web. Okay, but when Bing is asked this question, it goes one step further and gives the parse tree of this sentence, which makes the meaning very clear. So the parse tree is like this. As I said, you have to hit the main verb for a sentence. So these last three buffaloes, buffalo, 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 this is the verb phrase. And in this verb phrase, the first entity, buffalo, is the main verb. And buffalo, buffalo is bisons from buffalo. Okay. So this parse says that bisons from buffalo bully other bisons from buffalo. This structure. Okay. So buffalo, the subject is this phrase, buffalo, buffalo. What do? They buffalo, buffalo, buffalo. So this first set of buffaloes bully the third set of buffaloes here. And they are, of course, said to be bullied by other buffaloes from buffalo. Okay. So this is an acid test for any kind of parsing algorithm. If you're proposing a parsing algorithm, you will have to handle this sentence. This is one of those sentences which are challenging sentences for any parser. So Bing produces this parse tree and makes the meaning also very clear by referring to the ambiguity of buffalo. So this is an extreme example, but in real life, we do encounter sentences and phrases where ambiguity is always present. So this is an ambiguity. That buffalo example was a contrived example. Okay, it was not a real life sentence. But this is a real life example of ambiguity in operation and leading to breakage of communication between two ladies. Both these ladies, Lady A and Lady B, they are Bengali native speakers. They are also English educated. One more thing they do is that they do code mixing all the time. They mix languages all the time. So here is the conversation. Lady A WhatsApps to Lady B. Yesterday you told me about a shop that sells artificial jewelry. Ki naam jano. BN/BN. Ki naam jano. It's Bengali string. What did you say the name was? Lady B cryptically wrote NYKAA. Lady A gets offended and says, "What do you mean, madam? Is this the way to talk?" And Lady B is very surprised. Kano, ki holo? Why, what happened? Okay. And this Bengali native speakers will possibly understand what is the problem here, right? So the problem is that the spelling NYKAA, Nykaa, on one hand refers to this fashion shop called Nykaa, who are very successful business house in the fashion area. But NYKAA also is homophonous, has the same sound as the Bengali derogatory word Naka, which means a pretentious person. And it is typically not used in decent communications. That's why Lady A got offended. So what happened here was that there is NER ambiguity. Nykaa, is it a named entity or not? And then there is code mixing. If code mixing was not used, then that ambiguity, that pitfall could have been avoided. Okay. So Nykaa as a named entity has ambiguity with the Bengali word Naka. And that is happening because code mixing is being used. Now, code mixing, is a real challenge. It is a language phenomenon. In India, we use typically 2 languages and often 3 languages. I belong to Bombay, and people mix Marathi, Bengali, English, 3 languages. In Tamil Nadu, 3 languages. So NLP systems have to deal with this. So proper noun ambiguity, interestingly, has a pattern. Okay. It is many times the proper noun ambiguity comes from place people ambiguity. So India erupted in joy when Rohit Sharma and team defeated South Africa in the T20 World Cup final. India erupted in joy, not India as a place, but people of India. They were extremely joyful. And according to People's Linguistic Survey of India, India has the second highest number of languages, 780 after Papua New Guinea. Here India is a place. So named entity, those of you who work on named entity recognition would agree with me, there is a pattern to named entity recognition. And this pattern often is place, people, ambiguity. Okay. Similarly, if you take organization as a class, think about which are the most frequent classes it is confused with. Okay. Indira Gandhi Open University, Mumbai Vishwavidyalaya. These are organizations. What kind of ambiguity they can have, you can think of. But people, place, ambiguity is very common. So NLP layers are recognized. We have morphological processing where words are processed. And then we go through syntactic processing, part of speech tagging, chunking, they're called shallow parsing. Then parsing, this is called deep parsing. Semantics refers to meanings, and discourse, co-reference, pragmatics, they are at the highest level of the NLP stack. Now we come to the discussion of multilinguality, but do you have any questions, comments at this point of time? So I suppose this session will end at about 3:40, right? So let's delve into multilinguality. Multilinguality, the most basic concept in multilinguality is language typology, classification of languages according to structural features. So what is recognized in all languages is that there is phonology, phonetics dealing with sound, then morphology dealing with word, then sentence structure, this is syntax, and then use of these, and then meaning of the sentence, and then use of this meaning, which is pragmatics. So long back, linguists proposed what is called proto-language. Okay, proto-language means hypothesized language. So this was necessitated because people found a lot of sound similarity between languages which are even geographically far apart. So if you take Sanskrit and Latin, Latin is used in Europe, Sanskrit is in India, and the distance between those two geographical locations is at least 10,000 kilometers. So how come they share sound? 3 is Trayas in Sanskrit, Tres in Latin, 7 is Sapta, Septem, God is Devas, Devas. There is a lot of sound similarity. How this happened? This happened because Sanskrit and Latin descended from same source. Okay, some proto-language from which through branching we obtained Sanskrit and Latin. 3 basic entities in the sentence are recognized in all languages. We have subject, object, and verb. So these 3 entities, subject, object, and verb, give rise to 6 permutations. Object, subject, verb, subject, then verb, subject, object, and so on. And also there is a 7th possibility, which is no dominant order. Now, if you do a bit of investigation, you find that all these permutations have their representatives. So if you take SOV, of which Hindi is an example, V is the verb. The languages where verb goes to the end, Hindi is an example, that forms about 43% of all the languages of the world. Okay, SOV. What are the other languages of SOV? Bengali, Tamil, and so on. SVO, of which the most prominent representative is English. Here, verb is between subject and object. Then we have this permutation VSO, verb, subject, and object. An example language is Tagalog in Philippines. Okay, so what is interesting is that SOV, SVO, and VSO together form 90% of the languages of the world. So do you see anything interesting in this pattern? That 90% of the languages follow one particular constraint. What is that? What is invariant in these three permutations? Yeah, so subject is always before the object. Ram ne sham ko dekha, Ram sham ke dekh lo, Ram saw Ram sham. Subject is before the object. Why? 90% of the languages put subject before the object. The verb can take liberty, it can move around, but subject has to be before the object. Okay, so an interesting observation. I don't think anybody has explained why this happens. And people have hypothesized things, produced theories, but they have not been foolproof. And then you also have a no dominant order, which is Sanskrit. In Sanskrit, you can really take liberty with all words. And there is no problem with the syntax, either syntax or semantics. The other point is the geographical distribution of linguistic landscape. In India, we have the Indo-Aryan group, which is predominantly in the northern part of the country, a huge family. Okay, most of the languages are within top 20, 30. Hindi is within 10, within 5 actually. Bengali is within 10, Marathi is within 20. So these are large, very, very large linguistic groups, languages. Then we have in the south the Dravidian group, and in the northeast we have the Tibeto-Burman group, which is depicted by the red region. Then there are two languages called Khasi and Munda. Munda is in Choto Nagpur region. Khasi is in Meghalaya. Very recently, Google Translation System has also incorporated Khasi as a language. Khasi is not a scheduled language. That is, it is not an official language of the country. But Google has subsumed it in the translation system. So this is India's linguistic map. And that map again gives rise to this language tree, which is again a typology. So if you see this tree in the Indo-Aryan group, you have Western family, Southern family, and Eastern family called Shauraseni, Maharashtri, and Magadhi. And under Western group or Shauraseni group, we have Gujarati, Western Hindi. Under Maharashtra, we have Marathi and Konkani. So this is not only interesting linguistically, it is very interesting computationally also. This is the foundation for zero-shot learning and transfer learning. We have seen in our lab, we have lots of work on machine translation. Translation between Marathi and Konkani is a much easier proposition than translation between Marathi and English. Okay, so the languages which are siblings, okay, which are siblings under the common parent, often have their NLP systems much more easily built through transfer learning. So I can create a sentiment analyzer for Marathi, and it will produce reasonable accuracy for Konkani. A question answering system built for Gujarati will work pretty well for Punjabi. Okay, that is because of the linguistic properties they share, in particular the vocabulary. Okay, one of the signs that two languages are siblings, very close siblings, is 60 to 70% of the vocabulary is shared, either as such or through some transformation. Okay, so this is the basis for transfer learning. And in transfer learning, if you will recall, those of you who have read GPT series of papers, GPT-2, GPT-3, and so on, what is the philosophy of all these GPTs? What do they aim? You will see that the word generative pre-training is aimed at facilitating zero-shot learning, zero-shot and few-shot learning. Train with huge amount of data and use a small amount of task-specific or domain-specific data for fine-tuning, and the system is ready. Okay, so this kind of zero-shot, few-shot training is facilitated by language properties. Okay, language properties, and languages which are close to each other, their NLP systems are also close to each other. So we exploited this language tree, especially for Indian languages, Indic languages, and we had a paper in Journal of Machine Translation describing a data-driven machine translation amongst many, many pairs of Indian languages. So this was an experience paper. And those of you who are working on machine translation, I would strongly recommending reading this if you are thinking of Indian language machine translation. So this was multilinguality. And maybe the talking and lecturing is going on too long. It is time for maybe some demo, okay, which involves multilinguality. And I hope the demos will work. Okay, I'm always nervous before a demo. So this is the homepage of our lab, Computation for Indian Language Technology. And here there is demos under web services. So since I talked about multilinguality, let me take a interesting example of multilinguality in operation. Pivot-based machine translation. Pivot-based machine translation is used when the source and target language pair do not have much data. We do not have much parallel corpus to train. And this leads to data sparsity. To give you an example, suppose I'm translating from English to Bengali. Water in Bengali gets translated to, water in English gets translated to jal in Bengali, right? Now, suppose the training data doesn't have the water jal mapping. Now, if there is no signal or evidence in the training data, the machine learning model cannot manufacture that signal. This will lead to data sparsity in the test situation. Of course, you can use subwording, etc., but many times they fail. But what I have is I have English to Hindi mapping of water to pani and then pani to jal. So using this via media, I can get the mapping of water to jal. This very simple idea is the foundation of pivoting. And how is pivoting model? If you see the early papers of pivoting, it is based on statistical machine translation. That's why I say that linguistics and probability are the two pillars of NLP. So the fact that you can get language evidence through a pivot language is a linguistic point. Okay, so water maps to pani and pani maps to jal. So you get water to jal mapping also. But how is this mapping made precise? It is made precise through probability. And the foundation for pivot-based machine translation is the law of marginalization in probability. Law of marginalization is so important in probability. You can always introduce new random variables in the modeling through marginalization. You know that, right? Probability of A is equal to probability of A comma B, where B varies, takes values over all possible values. Okay, so you can always introduce a new random variable. Pivot-based machine translation is based on this fundamental idea. You introduce pivots and the corresponding random variables through marginalization. Okay, so it is instructive for all of us to read the theory of pivot-based machine translation. And how does marginalization take place in neural NLP? Okay, in neural NLP, all probabilities finally boil down to softmax computation. Okay, what corresponds to marginalization in neural NLP? If marginalization is the main tool for statistical machine translation, pivot-based statistical machine translation, then marginalization has to appear in some form in neural machine translation, pivot-based neural machine translation. How does it appear? Again, a thought exercise for you. So let's see. So we are discussing multilinguality and pivot-based machine translation. So let's see if I take English and then target language, let's say, is Hindi. One should drink plenty of water. This helps in hydration and maintaining body temperature. Okay. So I was just telling the class that before a demo, I'm always nervous. Will it work or not? So let's try. First is no pivot. Okay, translation has come. So बहुत सारा पानी पीना चाहिए. यह हाइड्रेशन और शरीर के तापमान को बनाए रखने में मदद करता है. Okay, but one should, something has happened to that. So let's introduce pivot. Hindi is quite close to Marathi. Does it change? Let's see. बहुत सारा पानी पीना चाहिए. यह जल योजन और शरीर के तापमान को बनाए रखने में मदद करता है. बहुत सारा पानी. There should have been an हमें, right? हमें बहुत सारा पानी पीना चाहिए. Or is it okay in Hindi native speakers? First sentence should be a subject. Huh? Okay. So Marathi is producing this. Now, the new thing which has come here is Jal Yojan. Hydration. Earlier I had hydration. Let's change the pivot language again. Konkani, if I take close to Marathi. बहुत सारा पानी पीना चाहिए. जल योजन और शरीर के तापमान को. It is Marathi is very close to Konkani. Same sentence. Let's take a pivot language which is completely different from both the languages. Let's take Tamil. Now subject is introduced. Okay. किसी को बहुत सारा पानी पीना चाहिए. यह सिंचाई is not at all correct. Okay. यह सिंचाई और शरीर के तापमान को बनाए रखने में मदद करता है. सिंचाई is not at all correct. Hydration. How about Gujarati? Will Gujarati help? किसी को बहुत सारा पानी पीना चाहिए. यह जल योजन और शरीर के तापमान को बनाए रखने में मदद करता है. जल योजन, is it the correct Hindi for hydration? Body remains hydrated. Does anybody know? Let's see. We can compare with Google and see. Or maybe IIT Bombay's machine translation system. This is under the Jal Yojan. Google is saying Jal Yojan. Then maybe we'll have to believe. Let's see what IIT Bombay system says. This is under the Bhashini project. Huh? खूब पानी पीना चाहिए. यह शरीर के तापमान को बनाए रखने में मदद करता है. It is eaten up hydration. Okay. What about the speech-to-speech translation system? So we are part of the Bhashini project, which is for speech-to-speech machine translation. One should drink plenty of water. It helps in hydrating the body and maintaining body temperature.
इसके लिए पर्याप्त मात्रा में पानी पीना चाहिए, जिससे शरीर का तापमान बनाए रखने में मदद मिलती है.
Yeah, hydration somehow is not captured, right? So this is the speech-to-speech translation system. Let me show you another demo in the same multilinguality motif. So these translation systems which I showed to you, the speech-to-speech system that I showed to you, it's a pipeline system. First speech to text, then text-to-text machine translation, and the translated text passes through TTS, text-to-speech. So this is directly from speech to text. directly, no intermediate text. Let me choose Hindi. खूब सारा पानी पीना चाहिए, इससे शरीर का जल योजन और तापमान बनाए रखना संभव होता है। Oops, why no audio input? Let me choose Bengali. বেশি করে জল খাওয়া উচিত। Drink more water, it says. Okay, and then if I take a more complex sentence, বেশি করে জল খাওয়া উচিত, এতে শরীরের হাইড্রেশন আর তাপমান বজায় থাকে। More water should be consumed as it keeps the body hydrated and the body warm. Warm, okay. So this is the kind of translation that comes out. Okay. So this is all in the theme of multilinguality. We have huge amount of work in translation and multilingual computation. Okay. Yeah, direct speech to text is only English, but speech to speech, there are many languages, and text to text, again, a number of languages. So here, for example, I can do English to Manipuri. I should also keep Google Translate ready. Okay, so Manipuri fonts are not installed in my machine. Is it doing a correct job? Let us see. So this is English to Manipuri. I'm giving the Manipuri output to Google Translate. Google has been dealing with Manipuri law for a long time. Detect the language. So this is Manipuri to English in Google. It produces a person should drink plenty of water. It helps in hydration and maintenance of body temperature. Wow. Perfect translation, you see. So that means English to Manipuri was very good. है ना? Okay. English to Nepali. Okay, I don't know if there is any Nepali native speaker, but let's get Nepali to English. This is Nepali to English. One should drink a lot of water. This helps in maintaining hydration and maintaining body temperature. Good. So this is Northeast languages. Okay, Northeast languages have tremendous data scarcity. So we are dealing with 4 or 5 Northeast languages, and that is an important goal of the Bhashini project, to bring languages which are less attended to under the umbrella of Bhashini. I think Northeast languages are doing well. Okay. So now we'll move to multimodality and more discussions, and then we'll also move to specific research work that we are doing in our lab. So at this point, any comment, question from anybody? We'll do 5 minutes more of discussion and then break for tea. Question, comment, anybody? Yeah. Ah. Oh, okay, okay. Good question. So if I have source target specified, and if there is data scarcity, can the system automatically suggest a pivot language? So you see, the pivot language is suggested considering two factors. One is linguistic similarity. Okay, so we once worked on English to Mauritian Creole machine translation. We had very little data, just 25,000 parallel sentences, laughably small. But the translation quality was not bad, mainly because we made a very correct decision about the pivot language. The pivot language was French. So French and Mauritian Creole are very close, vocabulary-wise, morphology-wise. And the other important factor is choose a pivot language such that one of the pairs is high resource. So English-French is extremely high resource. English-French pair is very, very fortunate. And English-French machine translation apparently exceeds professional translators' performance. So good there. So the choice of pivot-based machine translation should be based on linguistic similarity and resource abundance. These are the two factors. Now, can a machine automatically suggest? It's a very nice, beautiful question. If this should be your PhD topic. Any other point? Yeah.
It can help with the one word with the multiple meanings.
Ah, yes. Okay, your question is, can pivot language disambiguate? Yeah. Okay, it's a double-edged sword. Like many situations in natural language processing, any decision has its pros and cons. So when you introduce pivot language, the main goal is to solve the problem of data sparsity. I don't have water to jol translation, but water to pani, pani to jol exists. Now the problem is that when you introduce a pivot language comes with its own ambiguity. So in Hindi, I understand pani is ambiguous. Pani has multiple meanings in Hindi. So which meaning of pani should be taken? Now here again, probability helps. So if you have, if the pivot language is such that on the source side, you have huge amount of data, or even target side, you have huge amount of data, then the probability of water to pani and pani to jal, that probability is high with lot of data. So, but it is very possible that the pivot language brings in its own ambiguity and therefore noise. So you can have funny translations in pivoting. Okay, so we'll just introduce multimodality and then break for tea. So multimodal neural networks have this very characteristic architecture. Whenever you read any papers on multimodality, you will see there are 2-3 components on the input side, compartments on the input side. Typically, there would be a text compartment, then an audio compartment, then a video compartment. So here you have video, text, and audio compartment. So this is the first stage of processing. Then invariably there would be an aggregator. Okay, so you take the signals from two modalities pairwise and aggregate them, send it to the next layer. So between this pair and this pair, between this first and third pair, second and third pair, and so on, and send them to the next stage where there is an aggregation involved, and the final stage is the classification problem. So here, this network is, I'll describe this architecture and the work going forward. This architecture is giving a classification decision. What is the emotion of the input, which has audio, video, and text, all the modalities. And if this is in a conversational setting, it also decides this utterance has what kind of dialogue turn. Is it a question or affirmation or a plain statement or elaboration? Okay, dialogue turns have multiple classes. So which class is it? So this network is not only multimodal, it is also multitasking. So it is doing emotion recognition and dialogue turn classification simultaneously. So I'll talk about this work going forward. And multimodal architectures have this typical shape. Now, is modality required? It is required because NLP is becoming more and more ambitious. Many more things are being demanded from NLP systems. So if you look at these snippets from the very popular sitcom Friends, the second example, that is very amusing indeed. If you do not take signals from any other mode, this looks like a positive sentiment statement. But so the text is indicating agreement, but the audio has a sarcastic tone and the video has slight anger. So when you take all these modalities into account, it indicates sarcasm. No? Oh, that is amusing indeed. It's a sarcastic statement. So that decision is facilitated by taking into account all the modalities. And here's another example of sarcasm. Oh, great is a positive utterance, but look at the facial expression of the person. There seems like ridicule, sadness, everything in the face. So this is an indication of sarcasm. So all these difficult NLP problems corresponding to difficult language phenomena need multimodal signals. Okay. Now we come to this very important question of what is language modeling. Okay. And there was a question during tea time, can large language models solve all problems? To understand that, let us understand what language models do after all. So language modeling, before that you have to understand what does a model do. Okay. The model, the only thing the model does is prediction. So if you remember from your lessons in mechanics, the distance equation, S equal to ut plus half at square. So if you know the initial velocity of a particle, the time that elapses and the acceleration, then you can find out the distance that will be covered by the particle in time t. Okay. So S equal to ut plus half at square is actually a model. And the phenomenon it is modeling is the distance covered by a particle. That is the phenomenon. And given these u, t, and a, it can compute s, the distance covered. We say it is computing s, it is actually predicting, okay, s. Now, if you take u and a, if you know u and a, and if you are plotting s and t, okay, then by polynomial fitting, I think you will be able to come up with this formula, s equal to ut plus half at square. And then you will say that I have learned the model from the data. I have learned the model from the data. So now the same thing happens in machine learning, of course. So what does a language model do? A language model also does only prediction, and it predicts two things. First thing it predicts is the next language object. Given a sequence of language objects, it predicts the next language object. For example, if I take a question answering system, if I go to ChatGPT and ask this question, what is the capital of India? It says Delhi. So what it is doing is that it is predicting the most probable word after this sequence, what is the capital of India? It is just predicting the next most probable word. Okay. So this is not same as question answering. It is doing text completion. So one of the side effects of text completion is that an answer is coming for the question. So having seen these words, what is the capital of India? The next highest probability word happens to be Delhi, which has been learned from the data. And the next example is that of summarization. You have these 7, 8 sentences, and you have the summary as Delhi is a large, populous, and busy city. Here also, the next language objects are being predicted. The difference from the first example is that it is iteratively predicting words. Okay, it is predicting multiple words at different positions iteratively. So at this first position, Delhi is the highest probability word. Then the highest probability word is, then A, then large, and so on. Okay, so this is one thing which the LLMs are extremely good at. They produce the next word, next highest probability word, and it matches reality or the task. So this is one thing to keep in mind. Second thing to keep in mind is that language models predict the properties of language objects, again in the form of a text completion task. So if I give this sentence, the movie was wonderful, okay, and give the instruction prompt, give me the sentiment of this sentence, the movie was wonderful. And the ChatGPT comes back saying that this sentence has positive sentiment. Now, this piece of text, this sentence has positive sentiment, is also text completion. Okay, so that is the interesting part of this whole business. This is also being sampled from a probability distribution. At every position, I'm producing the next highest probability word. So LLMs predict the next language object and the property of the input object. The second problem is called classification. The first problem is called text completion. And if it is summarization, then it is sequence to sequence mapping. An input document is a sequence which is mapped to another sequence. So in this process, what the LLM or any LLM does is that it computes the probability of the next word given a sequence of words. Okay, so it computes a conditional probability. Now, in decoding the additional things, this is called autoregression, by the way. Okay, when you are generating the output, this is autoregression. So with that, if you also add the encoding of the input vector, the encoded vector of the input, then it is a sequence to sequence mapping. And additionally, if you include the self-attention and cross-attention, then also it is sequence to sequence mapping, but using transformers. That's all. Okay, so it is the core of all this is this probability of the next word given a sequence of previous words. Where does the power of large language models come from? The power of large language models comes from the long context, in context learning, and the long context. Two things: in context learning, which is this probability, the context is the conditioning part, and long context is this. So ChatGPT, we are told this part, the conditioning part, is about 4,000 words. Okay, so this is a huge dimension, actually huge dimension, because if you take the vocabulary size to be V, let's say 100,000 words in English, and if there are 4,000 words here, each of these positions can be filled in 100,000 ways. So 4,000, 100,000 to the power 4,000 is a humongous number, huge number. Okay, so no wonder the large language models are so powerful, because all this amounts to nothing but table lookup. You have seen this context before. You know the next word also from the data, and the large language model is just doing table lookup. That's all. Okay, so now there was a question during tea break. Where was it, you who was asking? So can large language models solve all NLP problems? Eventually, yes, because as and when the data gets created, all these new situations are absorbed in the training for the large language model. Okay, and because of the long context, because of all these data having been seen, natural language processing is now reduced to just table lookup. Such an anticlimax. No, NLP researchers are glorified people. Oh, I do NLP. And now if somebody comes and tells you, oh, you just do table lookup, that's all. How will you feel? It is table lookup. So this is what the large language models do. Now, the only limitation. We still maintain our glory because human mind and human activities are so creative. Okay, we invent new metaphors, we invent new ways of sarcasm, new language problems emerge. Okay, and then there are these texts which are uh, 2000, 3000-year-old scriptures. They have stood the test of time. And interpretation of these scriptures is a big task. Okay, interpretation of Shakespeare's poem is a big task. Eventually, that also will be done, I think. Some human being will interpret and put it on the web. This will become the training data for the large language model. In the next training phase, it will absorb this. Okay, so as long as human beings keep on creating new things, there will be newer frontiers to be conquered. But when human beings do not create anything more, large language models will solve all NLP problems. Okay, so do remember this point, that this probability value computation is nothing but table lookup where a probability score is given. So after this statement of mine, how many of you will still continue to do NLP? Will you or will you not? Or will you move to genetics or chemical engineering or civil engineering? I don't want to do any more table lookup. I'm done. No, the point is that this probability distribution itself is a very interesting thing. Linguistics and probability coming together produces lots of interesting things. Okay, so this is called the N-gram model. As you know, this is called the N-gram model. And N-gram models have this scars of dimensionality. We already saw that there can be vocabulary to the power n, where n is the context length, and the number of parameters is vocabulary to the power n. This is an extremely constraining and limiting situation, which is why statistical NLP had to give way to neural NLP. And the reason is this architecture. The reason is this architecture, that the language modeling in neural networks is done by softmax computation. So when you're predicting the next word, then you have a softmax layer here with the number of neurons equal to the vocabulary of the language. And this produces the next word given these n words here, which is nothing but language modeling. Okay, this is nothing but n-gram computation. Now here, does it suffer from the curse of dimensionality? No. You see the number of neurons here is equal to n into d into h. The number of neurons here is h into v, where v is the vocabulary size and there are v neurons here. And h is the number of neurons in the projection or hidden layer. And here v into n is the n into d into h is the number of connections from here. Okay, so and the number of biases is h plus v for these neurons. There are h neurons here, so h biases, v neurons here, so v neurons. Okay, so this language modeler, N-gram computer, the next word predictor, doesn't suffer from the curse of dimensionality. The number of parameters does not increase with the length of the input. Okay, which was the case for N-gram based models. So N-gram based models, after a point of time, begin to stress the decoder. Okay, the decoder is subjected to tremendous stress because it has to look for the correct string in an extremely large search space. This is not the case for neural language models. This is the contribution of Bengio, okay, who got the Turing Award with Lekan, creator of CNN, and applied it to ImageNet, and Hinton, the creator of RNN. I think it was 2021. So I hope this partially answers your question. Can LLMs solve all NLP problems? Okay, just reflect on this point of what do language models after all do? Predict the next language object. Now, did we have language model before? Yes. there were these context-free grammars which were supposed to do language modeling. Given the context-free grammar, by parsing, I can decide if a sentence belongs to a language or not. Okay. So here, for example, the gunman sprayed the building with bullets. Okay, it is a sentence from, this example is also from Christopher Manning's book on statistical NLP. So this piece of grammar is a language modeler for English, of course, an extremely small segment of English. Okay, and see the recursion here. This is left recursion. NP goes to NPP. That means a noun phrase can be composed from a smaller noun phrase and a preposition phrase coming after this. Building with bullets is a noun phrase. Building is a noun phrase. Building with bullets is also a noun phrase. So this is called, this is called generative grammar, which was proposed in 1960s by Noam Chomsky from MIT. So generative grammar was a tremendous step in linguistics and language processing. Okay, it paved the way for capturing the phenomenon that a language can have infinite number of word sequences. So this is called generative grammar. It generates infinite number of sequences from finite number of symbols and finite number of rules. Then came another instrument for language modeling. This is called noisy channel. So you have source sentence and the target entity here. This is a noisy channel for parsing of sentences. So source sentence comes in and the parse tree is produced from the sentence with a probability value. So this is the argmax computation, T star equal to argmax of probability of T given S. So choose that tree as the output which has the highest probability of T given S. Now you can apply Bayes' theorem and obtain PT, which is the prior probability, into probability of S given T. Probability of S given T is 1, because if the parse tree is given, then the sentence is completely determined. So it says that the best possible tree is the one, okay, which has the highest probability, which is very intuitive. Now from here, we come to another interesting observation, that the probability of a sentence is equal to sum of the probabilities of its parse trees. Now the probability of a sentence is the language model. So this is another way of language modeling, through a more sophisticated representation, the sum of the probabilities of the parse trees. And finally, okay. So I summarize the generations of LMs for the sake of completion of the concept. So the summary of the generations of LMs is, first generation is context-free grammar. Okay. Second generation, part A, is n-grams. Second generation, part B, is parse trees and their probabilities. And the next generation, the final generation, is neural language model through softmax at the outermost layer, a projection or hidden layer, and the input layer taking word vectors. Okay. And vectorization of symbolic entities is again a very important paradigm change in natural language processing. We went from symbolic representation to vector-based representation. That had the advantage of meaning similarity. So again, my favorite example is, take the three words cat, dog, and ant. CAT cat, DOG dog, and ANT ant. In terms of spelling similarity, which two words are more similar? Cat, ant, and dog. So which two words have more spelling similarity? Cat and ant. There are two characters which are common. And cat and dog, zero spelling similarity. But meaning similarity? Cat and dog. And cat and ant has hardly any similarity. Okay. So the moment you go from symbolic space to geometric space, the word vector of cat and dog are very close to each other because they have same distributional similarity. Cat and ant have a lot of distance between them, showing that they are dissimilar objects. Okay, so the surface level similarity is could be very different from the deeper meaning-based similarity, which is very effectively captured by vectorial representation. So this was a very important step in NLP. Word vectors is a paradigm changer. So LLMs, all they do is predict the next word and fill in the gaps. They make use of self-supervision. Okay, training of large language models in terms of annotation is very, very cheap. You just take corpora after corpora. Okay? Take a part of the sentence, rest of the sentence is the prediction. So this is called self-supervision. And all you need is huge amount of data and many GPUs. They have huge number of parameters. OpenAI has 1 trillion parameter machine to 4 trillion parameter machine. Sorry, huge number of parameters, 1 trillion to 4 trillion. 1 trillion is OpenAI's GPT-4, and Amazon's Olympus is 4 trillion. Now there is an interesting observation. The Olympus expenditure is about $4 billion, which is 33,000 crore Indian rupees. The state of Goa has a budget of 25,000 crores. Okay, more than the budget of a state, small state. This is an interesting perspective. So these are very expensive propositions. Now, applications are created by piggybacking on LLMs. So we go from least expensive method of system building to most expensive. Prompt engineering doesn't require any resource. Okay. Adapter network, you have to take a small fit for a network and train it, not much resource requirement. Fine tuning requires more resource, and pre-training is not everybody's baby. Huge amount of computing resource, huge amount of data required. But in terms of resource requirement, lower to higher is prompt to adapter to fine tuning to pre-training. There are 3 stages of LLM-based conversational AI agents: generative pre-training, supervised fine-tuning, reinforcement learning based on human feedback. These things you were aware of and you know of these stages. An interesting fact is that OpenAI advertises for AI trainers. Okay, one of my students recently got a job with OpenAI, and his only job is to serve as AI trainer. That means test the GPT-4o to see whether it answers all the questions correctly. And there is a test suite of questions, of course. If it is not correct, then he has to give the correct response. So, and paid very handsomely for this. Okay, so apparently there are about 4,000 to 5,000 AI trainers all over the world. Their feedback passes through reinforcement learning based framework and then changes the model appropriately. So evolution of LLMs took place this way. In 1960s, we had perceptron, a single neuron. 1984, feed-forward network and backpropagation. Recurrent neural networks in 80s. Attention came in 2015 due to the work of Bahadanu. Transformers in 2017. It introduced positional encoding. And then LLMs through GPT series in 2020s. This is the chronology. But we must understand that language models are very old, at least 2000 years old. The notion of grammar existed in all languages, but not in the form of generative grammar. Okay, it is interesting. We do not know yet if the ancient grammarians or in the ancient culture did the idea of recursion exist. We do not know. Iteration, fine. Did recursion exist? I don't know. We do not see any evidence of generative grammar in Panini's framework or Saussure framework and so on. 1960s, Chomsky gave generative framework by making use of recursion. Generative framework is this context-free grammar rules. Context-free grammar rules, okay? And if you introduce recursion, it can generate infinite number of strings. Yeah. I think recursion existed, but it was not made explicit in before 1960s through generative grammar. Okay, so this is the timeline for language model in a different perspective. N-gram models and 1948. The 1954 distributional hypothesis, recurrent neural network 1986, 2013 word vectors, word to vec, 2014 attention, and 2017 transforms. Now, one phrase which I am trying to popularize, okay, and I'm a evangelist for this phrase, Trinity language models. Large language models are difficult to create, but almost anybody with some amount of resource can create domain, task, and language specific models. Okay, for example, domain is agriculture, task is question answering, language is Konkani. So this is a question answering system for farmers in Goa who have questions regarding price of commodities, weather, and so on. The internet connection is unstable, it says. Okay, that's okay. So these Trinity models can be built by anybody, any small organization. That connection is still there or not? It is there, okay. So from our lab, I give 3 instances of Trinity models. We are working on what is called a legal llama project. This is in collaboration with Meta and National Law School of India University at Bangalore. This is a law university. So, the idea is that the Ministry of Commerce would like to automate, have AI agent for addressing consumer grievances. Okay. Now, consumer legal affairs take up roughly 4% of the legal actions taken in India. As an aside, does anybody know which cases consume the maximum amount of time in courts? Which is the largest number of cases? Any guess? Property, land. Any other guess? It is so trivial that you will bring it to, huh? Family? No. Traffic violation. Okay. 80% of the cases in the court are traffic violation cases. Okay. So if you dispose them off, huge amount of time and energy of the court is saved. Okay. And we are told 4% of the legal actions are consumer related cases. So we have been asked to create a question answering system. So I tried the following thing. I asked ChatGPT, I bought a new car in Mumbai and its brake is malfunctioning from day one. The company whose showroom I bought the car from is not listening to my complaint. Can you tell me how I can have my grievance redressed? And ChatGPT answers this. First of all, it is trying to be very nice with me. Dealing with a malfunctioning brake in a new car can be frustrating. I know this, of course. Especially when the company isn't addressing your complaint, here are the steps you can take. Now it gives very general instructions. Document everything. Then review the warranty and consumer rights and contact customer service. It gives some 6-7 such instructions. They are not really of help. Okay, what is of real help is what is there on the Department of Consumer Affairs website. How to approach National Consumer Disputes Redressal Commission. Okay, ChatGPT did not tell me that there is such a commission. Then I also know that I can appeal against the state commission to national commission. I can also appeal against national commission in the Supreme Court. So this is what is told to me by this website information. It also tells me very specific information like what is the court fee, 5,000 rupees. And the appeal to Supreme Court has to be made within a period of 30 days from the buying of the article. Then it gives me a table of who doesn't have to pay any fee, for whom is the fee only 100 rupees and so on. This is called specific helpful information. Okay, what ChatGPT gave me was very, shallow kind of help, which is not really a help. It is a kind of pacifier, I would say. So this is, by the way, very characteristic of large language models for extremely specialized domain-specific question answering systems. This we have seen in medical domain. and now in law domain. And it has been reported that large language models are not doing well when it comes to very expert kind of help. So what was surprising to me is that this was always available on the website, and I'm sure GPT-4, GPT-4o has seen this data and must have trained on it also. Then how come it is not producing that answer? Possibly the paid version does produce that answer. So we have to create a citizen-centric chatbot, a decision assisting tool. And of course, we are using fine-tuning and retrieval augmented generation. Lots of NLP problems are solved, have to be solved in this project: translation, information extraction, case similarity, clause application. So this involves entity relationship extraction, document classification, paraphrasing, text entailment. Many NLP problems are involved here, but large language models seem to be solving all these problems together under one umbrella. Another project we are doing is for railways. We call this Rail LLM. It is in collaboration with Center for Railway Information System, CRIS, and again with Meta. So here the goal is to create smart chatbots which answer questions with respect to train schedules, fares, platforms, and so on. That's a very obvious help. And then providing translation services. Railways have not done it yet, and so we are interacting with them. Maybe the Bhashini resources will be used for this. So people travel from Manipur to Tamil Nadu, let's say, and huge amount of translation need exists there. The other problem is that the railway passengers write a lot of things about railway services in the social media. And there are so many such cases, it is impossible without an automation to keep track of all these complaints and all these comments. So again, they want an AI agent to do this feedback analysis and would like to have improved complaint handling, mainly because of the scalability and robustness angle. The third problem is making use of, again, Llama, the large language model. This is enhancing government transparency and citizen engagement with chat applications. The problem statement is to build an LLM which answers queries related to resolutions passed by Maharashtra government. Okay, so you make queries in Marathi and they get answered. Again, I have a demo for this. If time permits, I'll give you that demo. So, well-known LLMs are like GPT-3, BERT, ExcelNet, T5, Llama 2, Olympus, Mistral 7B, OpenHathi, Palm. I think many of these language models you have used for your work. And you see the number of parameters: 34 billion, 4 trillion. 4 trillion is the largest number of parameters. Mistral is 7.3 billion. GPT-3 is 175 billion. BERT, which is most popular, probably 110 million. You can use BERT in your local machine. Okay, now interesting comparison with human brain. The number of parameters in human brain is about 600 trillion. How do I come to this figure? Human brain has 8.6 into 10 to the power 10 neurons. That is 86 billion neurons. And each neuron has some 7,000 synaptic connections. Hence, the total number of parameters on an average is 600 trillion. 600 trillion in human brain, and Olympus from Amazon, 4 trillion, which is the largest number. Another comparison is on energy requirement. Humans approximately consume 175.2 kilowatt hour per year. The annual energy consumption is about 175 kilowatt hour. A typical household in India consumes about 3,000 kilowatt hour per year. GPT-3 consumes 1,647,000 kilowatt hour of energy per year, which is about 10,000 times that of a human and about 500 times that of an Indian household. So do you see the seriousness of the comparison here? As human beings, which are like epitome of intelligence, computational machinery, large language models are trying to reach our level. Okay, but the energy consumption is 10,000 times annually. And the carbon footprint, the amount of pollution they create. Okay, our carbon footprint is 4,500 kg per year per person. CO2e means equivalent of carbon dioxide. Okay, so we pollute to the extent of 4,500 kilogram of CO2 equivalent per year per person. GPT-3 is 430 to 680 metric tons. That is 430,000 to 680,000 kilogram per year, which is about 100 times. Okay, so carbon emission from large language models is 100 times, energy consumption is about 10,000 times. And how many times intelligent they are compared to us? Okay, interesting question to ask. We still beat them, right? But let's see how the world shapes up to be. So some interesting aside from neurophysiology, as far as language processing is concerned, there is one area of the brain called Broca's area. The damage there messes up the syntax. So you would say things like I eat rice spoon to mean I eat rice with spoon. So Broca's area damage patients have this typical behavior, they drop function words. Also, they cannot distinguish between visit to the president versus visit by the president because the function words are ignored. There is a complementary area in the brain, it's called Wernicke's area. The damage messes up the semantics and pragmatics. So you can have very fluent and meaningful but meaningless phrases. The pink elephant sang and the blue stone danced. This is semantically impossible, but syntax is perfect. Okay, so Broca's area, Wernicke's area are two important areas in the brain for language processing. Now, academia at many enterprises and industries are going back to small language models. Okay, small language models hardly consume any resources, but they solve problems very well. So Llama 2 is 7 billion, Phi2 and Orca 13 billion, Stable Beluga 7 billion, small language models. XGen 7 billion, Alibaba's Qwen series also has 1.8 billion, 7 billion, 14 billion, 72 billion. Alpaca is 7 billion. MPT 7 billion, Falcon 7 billion, Zephyr 7 billion. So you might have noted the most of the language models are using 7 billion parameters. So again, I like to make this statement. I made this in the class also. How come 7 so frequently? 7 appears again and again. And 7 is a very important number, right? There are 7 C's. During marriage, we do Sat Fera, 7, right? So again, 7 has appeared in the field of large language models. 7 billion parameters. 7 colors in the rainbow. So there must be something mysterious about 7 billion. For the number 7, there must be some inherent power in it. Okay. So language models and conversational AI are close to each other. One of the success stories of LM is conversational AI. Now I'll hurry a bit. We have to finish at 5:15, right? So chatbots are very important, and it is said that the chatbot market will be worth $27.2 billion by 2030. Okay, a very important technology. And what is happening is that the chatbots are also replacing lots of human beings. For example, Indigo's WhatsApp bot Dotty, it tackled 86% of the chats and transferred 14% only to experts. Okay, there is a startup called E6 handles 91% of the chats. The number of experts needed is down to 69 from 107 before. So chatbots are indeed taking the jobs of human beings. That's true. But creating other job opportunities. So there are many pitfalls: data residency, privacy, complexity of real-time information, complexity of novel data streams, hallucination, lack of emotional intelligence, lack of empathy, and so on. So there was this curious case, an AI chatbot was caught telling business to break several laws. For example, this chatbot in New York said that it is okay to fire employees who complain of any kind of harassment. Then it also said that it is okay to eat cheese that has been eaten by rats. Okay. Only thing is that we have to ascertain the extent of damage that the rats have caused. After that, apparently, we can eat that cheese. So these are wrong instructions and maybe harmful instructions. So the solution to pitfalls is that we have to make use of multiple models like BART, ChatGPT, etc., and reconcile the answers from many different sources. Okay, and the emerging world order we see is human-machine synergy. Okay, so the linguistic foundation of CA, I don't think I'll go into. What I'll do is that let me take up some work of ours. Okay, otherwise I'll miss them. So the computational perspective of conversational AI is that we perpetually keep on solving a classification problem. So here is a conversation between two people, A and B. A says, so do you go to college right now? This is a yes/no question. And then he says, are you, and then abandons the statement. So this is called, this is given the label abandoned. B says yes. And the label here is yes answer. Then he says, it is my last year, which is a statement. Also, there is a laughter note there. So dialogues are often accompanied by emotion. Okay. So dialogue turn classification is an important NLP problem. You have to classify them as a question, a statement, or a request for action. And there has been quite a lot of prior work on dialogue classification. So what we did was we tried to do emotion analysis and dialogue turn classification simultaneously, and showed that this kind of multitask handling of the problem increases the accuracy of both tasks. So sentiment analysis is an important area, sentiment and emotion analysis. Sentiment analysis is rigorously defined by means of a 5-tuple. The third entity is most important, the sentiment of an opinion holder at a time t with respect to a feature of an entity. So to give an example, if you have this sentence, I love the songs in a movie, though only the cast was liked by my brother, who said the director was of the opinion that the storyline, which is from a novel by Shakespeare, will be lapped up by the public. So the entity here is movie, and there are many features, songs, cast, storyline. And who is loving what or hating what is recorded here. I love song, brother like cast, director like storyline, and public lap up storyline. So this kind of triple formation is very crucial when we do aspect-based sentiment analysis. Now, sentiment analysis has many dimensions, the language dimension, the feature dimension, the output dimension, the resource dimension, what is the machine learning technique which is used. These days, of course, everything is based on large language models and deep learning. Now, sentiment analysis is typically a 3-class classification problem: positive, negative, and neutral. Emotion analysis is a multi-class classification problem. There are finer classes like anger, disgust, happiness, and so on. And many emotions are confused with one another, okay, because their signals are very same. Anger and disgust, for example, would have similar kind of words used. So basic emotions are 2, actually, happiness and sadness, which has been known for thousands of years. So a psychologist called Ekman gave these 6 classes for emotion: anger, disgust, fear, sadness, happiness, and surprise. This has become computationally very important. NLP researchers have been using Ekman's classification for a long time. But then Plutchik's emotion came with many interesting possibilities. So he gave 8 basic emotions. And in India, we have this tradition of Navaras, 9 emotions, which are love, mirth, fury, compassion, disgust, horror, terror, heroism, and wonder. So Plutchik's wheel of emotion is a very interesting framework. The basic emotions are here. For example, this is trust, this is fear, this is joy, and so on. So when you go from any point towards the center, the intensity of the emotion increases. For example, for joy, the intense form of emotion is ecstasy, and lesser intensity emotion is serenity. For fear, terror, and apprehension. Okay, and also between two petals, you have combination emotion. For example, trust and fear is submission. Joy and trust is love. So Plutchik's wheel of emotion is a very nice framework because it allows you to synthesize emotion annotated data. So if you have data which is annotated with trust and fear, then you can synthesize data which is annotated with submission by taking maybe 40% of trust and let's say 60% of fear, which is submission. So you can do what is called emotion vector-based arithmetic, combination, subtraction, and so on. So we have some work in that area published in Interspeech. So we have been working on emotion and sentiment analysis for a long time, since 2000. And we have adopted all forms of machine learning paradigms, rule-based, classical machine learning, deep learning, hybrid. And all these are many different problems of sentiment and emotion analysis. So initially we started with basic sentiment and emotion analysis in 2000, then moved to thwarting, sarcasm, emoji-based sentiment analysis, cross and multilingual sentiment analysis, and sentiment and emotion analysis in dialogues. So we have a very long line of work since 2000, and all these have been published in top fora, okay, for a very long time and very steadily. So now let me show you some challenges which exist for sentiment analysis. First challenge is sarcasm. I suggest you wear your perfume with windows and doors shut. This is a sarcastic sentence suggesting that your perfume is of not good quality. Then this is very intriguing. So and so falls 284 runs short of what could have been a first class triple century. How much did the person make? How many runs did he score? Falls 284 runs short of triple century. 16. No? And such a colorful way of saying that he made only 16 runs. So this is implicit knowledge. Thwarting is where you have lots of positive sentences and then one damaging negative sentiment. So the overall sentiment is negative. Then the language could be strange. Then the same word can mean both positive and negative sentiment. He is a deadly football player. It is an appreciation and positive sentiment. You may have deadly snakes at the campsite at night. So there is a negative sentiment about the campus. So these used to be big challenges 15 years back when we were doing sentiment analysis. These were the hurdles in front of sentiment analyzer. The ChatGPT laughs at all these examples. It detects all these as what kind of sentiment. You give this sentence, it says it is a sarcastic sentence. You give this sentence and asks what is the meaning of this. ChatGPT comes and says that the person made only 16 runs. ChatGPT does this. So none of these challenges, which were real challenges 15 years back, are no longer challenges. So this possibly answers your question a bit, that NLP's hurdles are being tackled every year by these LLMs and new developments. So we have a comprehensive research program. Initially, we were working with text, then came to speech, image, and video. We added these modalities. Initially, we were doing emotion and sentiment analysis only for English, and then Hindi, code mixing, and other Indian languages and European languages also came in. Initially, we were doing only sentiment analysis. We also transited to emotion analysis, joy, anger, fear, surprise, etc. And one thing we are exploring now quite deeply is how to capture the Navarasa system, the 9 emotion system of India, okay, which is very accurate and very comprehensive. So you see this dancer in dance and acting. The dancers, actors, they are trained to depict all these emotions very faithfully. It is their business to depict these emotions. And interestingly, each of these emotions have a color associated with them, which could be the, a signal. And also they have a presiding deity. For example, for Hasyaras, laughter, the presiding deity is Shiva and the color is white. So how is sentiment analysis modeled? It is again modeled by this argmax computation. E star is argmax probability of E given F, where F is the text, E could be the emotion. Okay. And if you apply Bayes theorem, then you get two parameters, prior probability of emotion multiplied by likelihood of the text given this emotion. Okay, this is the regular argmax based modeling. So we had a piece of work in 2020, which is a good example of multitask and multimodal, emotion analysis. So very quickly, we had to give a framework which would detect the emotion and the dialogue turn simultaneously. So the labels for utterances were answer, statement, agreement, disagreement, and so on. And emotion were neutral, sadness, anger, fear, etc. So what we did was we took a standard data which is called IEMOCAP. Okay, that had emotion labeled dialogues. We added dialogue turn classification on that data and thereby got a multi-labeled data set. And then we gave a framework which I showed before, which had video, text, and audio in the input, and there was an aggregator, and it did dialogue act classification and emotion classification together. And we showed that if we do this multitask framework, then the accuracy is much more than single task framework. Also, if we use multi-modality, okay, text, audio and video all together, then also the accuracy improves. Okay, so the main message of the paper was that multitask and multimodal framework, they help. And this was also qualitatively verified. Now, last year, we had again a multitask framework for a very challenging problem, that is hyperbole and metaphor detection. So here what happens is that in case of conversational AI, the chatbot has to deal with these language phenomena, hyperbole, which is exaggerated statement, and a metaphor. Okay, so the principal is angry. It doesn't have any hyperbole or metaphor. I will walk 1,000 miles to meet you. It has exaggeration, that is hyperbole, but no metaphor. Life is a journey, doesn't have hyperbole, but it is metaphorical. The principal is going to cook us for the first sentence. It has both hyperbole and metaphor. Okay, and let me see if I can give a demo to you. Hyperbole and metaphor detection. Takes a bit of time though. If I enter this sentence, this should not have any hyperbole or metaphor. Okay. It takes a little time. Meanwhile, let me keep a sentence ready. Yeah. So, oh, that's wrong. How come? There is the capital of India hyperbole probability 0.9, 0.89. No. I don't know. 1 minute. Huh? This has both metaphor and hyperbole. Erupted in joy, the reference is to a volcano, something erupting. And erupting is also exaggeration. It has predicted hyperbole probability 0.936, metaphor probability 0.994. Let's look at the explainability a bit. So the dark areas are where attention is highest. This is too small for me. Yeah. So India erupted in joy when its cricket team won the World Cup. Okay. So we see high attention given to when it's erupted should have been high, but not very low here. And this is in the single task model. And in multitask model, erupted has very high attention, see, very dark. Okay. Right. So, yeah, it should not have given hyperbole and metaphor high probability for Delhi is the capital of India. We'll have to see what is happening. Okay. So, this was again a linguistic insight that hyperbole and metaphor often go together. Okay. You create metaphorical statements with exaggeration many times. So then we say that why not do these two tasks together? And the practical utility of metaphor is very much there. Here is a hypothetical conversation. So the conversational AI asks the human being, "How was your day?" And the human being says, "It was raining profits today." So the chatbot says, "Oh, remember to take an umbrella next time." Did not catch the metaphor. I meant I made a ton of money. That must have been heavy. And then the human being sighs. So this is true, right? Conversational agents still do not have the capability to capture those colorful languages. So here we did multitasking. We had three architectures, single task architecture. This is doing hyperbole, this is doing metaphor separately. And this is a shared encoder, but the classifiers are separate. In this case, both classifier and encoder are shared for metaphor as well as hyperbole. And I'm just showing the numbers. We use standard data sets. You can see here the F score is high for multitask learning. Okay, this is for one data set, and this for the other data set. Again, we see that multitask learning achieves higher figure. For this for hypo data set, this for hypo L data set. Okay, so this again is a case for multitask learning. Then one of our this year's ACL paper is on pragmatics and LLM. And pragmatics is a very difficult problem in NLP. It is at the highest level of NLP stack. So the meaning of pragmatics is that it is meaning in a context. It should be contrasted with lexical semantics, which refers to word meanings. And sentential semantics also is different from pragmatics. Pragmatics is always extra sentential. So here are some examples. Suppose there is a dialogue or conversation happening between speaker A and speaker B. Speaker A says, "Shall we go for a walk?" Speaker B says, "It is raining outside." The implication is that the speaker B's answer is no. So we wanted to ask, can LLMs catch these implications? That was the main study. And another example, the person entering a room where there is an AC running, "Isn't it cold here?" So the answer, the intended answer is not yes or no. It is an action. Go and stop or reduce the AC. Okay, so this is the role of pragmatics. Pragmatics is always extra linguistics. It is beyond the sentences and the paragraphs. So pragmatics is language in use. So for example, a priest is conducting a wedding ceremony in the church. The uh, the protocol there for the priest to say the following sentence: I pronounce you man and wife. So is he pronouncing something? He's pronouncing, but the actual effect is that the man and the boy and the girl gets married, and it is solemnized. So there are many elements of pragmatics. Each of them is a challenge for NLP. First is deixis, which literally means pointing with words. There are temporal deixis like now, then, special, here, there, personal, I, you, he, they, etc. Now, binding these deixis to actual language phrases is a very, very complex problem in NLP. Then presupposition. If I say untie the shoe, this means that the shoe was tied before. Okay. Then speech acts. These are locutionary, illocutionary, and perlocutionary. We don't have time to go into those details. Implicature, I showed you just now. Walk, taking a walk. Politeness is also a pragmatic element. Close the door is statement. Please close the door is more polite. Can you close the door? Still more polite. Would you mind closing the door? Is still more polite. So politeness is also extra linguistic. It comes with the sentences. Information structure is a very intriguing cognitive situation. Suppose there is this flask on the table. Okay, do we say that a flask is on the table? Do you ever say the table is under the flask? Do you say? You never say. Why? Okay, this is called information structure. Okay, though the meaning is same, the flask is on the table, but we never say table is under the flask. So this is also a pragmatic concern. So what we did was we tried to investigate the pragmatic capabilities of LLMs, and we tested many LLMs with the following task. Input is context, question, and option, and the output is a correct option in the form of multiple choice questions. So data set for 14 distinct tasks in pragmatics, we contributed this data. This data is open. A systematic evaluation of 6 variations of Llama 2, T5, FLAN T5, and GPT 3.5, and a comparison of these LLMs with human performance. So, and we use 2 kinds of prompting, closed prompting and multiple choice prompting. So what was the task? Here is the task. The context is this: speaker A, shall we go for a walk? Speaker B says it is raining outside. Then there is a multiple choice question to the LLM. Question: which of the following is true? B agrees to take a walk. B disagrees to take a walk. B's intent cannot be determined. B did not answer. Okay, this is what the LLMs are supposed to do. This is implicature. Another, there are many such tests. Another test was this: presupposition. Context is this: speaker A says, did you untie your shoe? Speaker B says no. So MCQ, the question is, which of the following is true? B had tied his shoe before. B had not tied his shoe before. B's prior action cannot be determined. B did not answer. So LLM is supposed to pick the correct choice out of this. So what was the result? I show it for implicature first. So we see that for let's take this middle one, implicature recovery in dialogue, which was the situation that I presented. Can you get the implication in the dialogue? So here we find that Llama 2 with 7 billion parameters has accuracy of 56.26. Llama 2 70 billion, the accuracy jumps 56 to 75. Human performance is 93. Okay, far ahead of all the LLMs. And if we go to presupposition, question answer over presupposition, here again Llama 2 7B is 53, 70B is also 53, not very much more. And human performance is 67. You see, this task is difficult even for human beings, the presupposition task. And if you compare this with human performance, then we see that Llama 2 70 billion goes close to human performance. And also this FLAN T5 XXL also approaches human performance. And that is mainly because FLAN T5 XXL is trained on huge amount of natural language inference data, text entailment data, many of which actually capture pragmatic phenomena. So this was a piece of work we did under LLMs, testing of LLMs. And I'll finish with this work, which was also in this year's ACL, Indian language information retrieval. So here we note that neural information retrieval has the following characteristic. Queries and documents both are represented as vectors. The vectors can be static word vectors or contextual word vectors. Okay. And then it is vector-based similarity, which gives the ranking of the retrieved document. So this is again from one of our work, which is in the area of AI for society. So if the query is girl education and there are 3 documents, women education reduces inequality, there is a girl from Lucknow, and document number 3, women in STEM are provided scholarships. For this query, the most relevant documents will be document 1 and 2. Keyword-based search produced second document as the highest ranked document because it did not catch the similarity between women and girl and education and STEM. This problem was pretty well solved by vector-based search, namely neural search, mainly because the words are points in the multidimensional space. So indeed, when we gave this query called education, a neural search system gave a high ranking to the third document. Women in STEM are provided scholarships by India government. So this has a 2-stage search architecture. First of all, the query goes through an approximate nearest neighbor search. Okay, and then there is a re-ranker, which is based on cosine similarity. So this is the architecture. The baseline is BM25 algorithm based on keyword search, and vector-based algorithm is dual encoder and cross encoder. In dual encoder, the query and the document are presented separately. In cross encoder, the query and document are concatenated with a separator between them. Okay, and one string is presented. So our literature survey showed that BM25 is a very good baseline to compare with. And if you take, let's say, the TREC dataset, which is a shared task for information retrieval, testing of information retrieval algorithm, BM25 gives a figure of 0.506 in NDCG, and recall at 1000 is 0.739. Neural systems have better figures for both. And Colbert is a very standard system now. It achieves the highest level of performance. Okay, so I'm sorry to be rushing through the numbers, just to show that the world is moving towards neural search engine, Colbert model. So what we did was we wanted to say that why not Indian languages also have neural search. So we based our work on Colbert. So Indian language information retrieval has this characteristic. Large generic data set, small in-domain data set, small in-domain data set. This is for English. And in Indian languages, we have small in-domain data set. Our goal was this. We would ask a query in one language. Information retrieval model will retrieve documents in all languages. Wherever the information is, fetch that document. So query could be in Hindi, and document in English, document in Bengali, document in Hindi. A characteristic situation for this is newspaper search. Okay, Indian cricket team's performance in T20 World Cup. So many different newspapers report this news item, and they look at it from different perspectives. So why not bring all the documents for all languages and then run multilingual summarizer to produce a gist of what is retrieved? This is a very practical and useful problem. So we addressed this problem, and we did the following contributions. We had created a data set called Indic Marco, which had 1 million queries. Documents were 8.8 million. Training triplets were 39 million. And number of languages were 11. So this is a massive data set. We have made it open through this ACL paper. And Indic Colbert, it's a collection of 11 models. Okay, 11 neural information retrieval model. We call this Indic Marco. And the improvement over baseline is 47%, 47.47%. For Bengali, the improvement was 20%. This is for Bengali, and this is for Hindi, 12.26%. These are different benchmarks which are available in the field. So, we apply lots of translation on existing what is called MS Marco data, and the translation process itself was a large piece of work. So we call this Indic Colbert, where document vectors are created, they are encoded, queries are also encoded, and then a score is computed making use of the Colbert formalism of Maxim. So the numbers here, Colbert models trained on Indian language data. For Assamese, it achieved a performance figure of 0.7, Bengali 0.7, Gujarati 0.8. So it hovered in the range of 0.7 to 0.8 for various Indian languages. Okay, and here is a bit of analysis. No improvement could be seen for Oriya because the MBART used in Indic Colbert is not pre-trained on Oriya and Assamese. Assamese demonstrates a 125% MRR at 10. MRR at 10. MRR at 10 is a performance figure improvement over BM25 baseline attributed to its linguistic similarity with Bengali. So this is interesting. So there was no pre-training on Oriya, so Oriya's performance improvement did not happen. There was no pre-training for Assamese. Okay, but Assamese and Bengali are close. So I was mentioning to you language typology and sibling. So Assamese figure was pretty good, most probably because it made use of the pre-training of Bengali on the neural model. Okay, so this was a piece of work which contributed a lot of data, many models, and hope this will facilitate information retrieval research in Indian languages. I end with the responsible AI. We know that large language models suffer from toxicity, hallucination, cyber scamming, deep fake, companionship, bias, the question of AI filing patents, and there are many vexing and serious examples of AI going wrong. So we try to contribute to solving the bias problem for Indian languages, LLMs. So we created a benchmark called Indic bias, and this was reported in NSL 2024 this year. So the contributions were, we quantified bias in several dimensions: gender, religion, caste, age, region, physical appearance, and occupation. We also introduced the very complex problem of intersectional bias. If we have multiple biases at the same time, gender bias and religion bias, okay, then gender and age, and gender and caste. So our the contributed data actually captures all these bias situations, and we did empirical analysis using our data set for building models. So this was another piece of work. So let me conclude my talk. So we covered foundations and applications, multimodal and multitask emotion and dialogue, metaphor and hyperbole, pragmatics and LLM, neural IR. Okay, some of these applications we covered, which are based on our lab's work. Then LLMs and generative AI definitely have opened up very promising new directions, but with power comes responsibility. We also have to address the problems of bias, hallucination, profanity, hate speech, etc. And we see that small language models also have a role to play. They are becoming more popular, mainly because of RAG. Okay, you can create knowledge graphs, knowledge bases, and also even raw text, which can be injected into small language models. And they're competing well with the large language models for a number of tasks. So this is a very, very redeeming feature, a situation for joy, okay, for researchers. Not everybody can afford large language models, but small language models along with knowledge graphs, that is retrieval augmented generation for small language models, is the way to go. So this is our lab's homepage. I showed this homepage during demonstration. Everything I have said is, at least all our research papers are linked from my homepage. Resources are contributed to our lab's homepage. And then let me thank you.